Welcome to Chapter 01, Radiation Basics, brought to you by Radmaster Information Services LLC. The abbreviations above are extremely common in the physics world. It is recommended you memorize them. Let's talk about energy. Objects can carry energy by virtue of their speed or their position. A stretched spring or lifting an object are examples of giving an object potential energy which can be retrieved by releasing the spring or dropping the object. The smallest thing that is sugar is the sugar molecule. You can break that molecule into parts, but it won't be sugar anymore. The sugar molecule can be divided into atoms, but individually those atoms are not sugar. Like our alphabet has only 26 unique letters which can be used to express any English word. There exists only 118 unique atoms, and of those only 92 exist in nature. All the world's many types of molecules consist of combinations of these 118. Our simplified model of the atom contains protons, neutrons, and electrons. Either protons or neutrons are known as nucleons. The atomic nucleus at the center of the atom contains protons and neutrons and contains almost the entire mass of the atom. Protons live in the nucleus or center of the atom and have a positive electrical charge. Neutrons also live in the atom's nucleus. Neutrons have no electrical charge and have a mass almost identical but slightly larger than the proton. Electrons are found outside the nucleus and only in designated locations called shells. The electron has a negative charge, equal to but opposite to the charge of the proton. Electrons have a very small mass compared to the proton or neutron. It takes the mass of almost 2,000 electrons to equal the mass of a proton. The periodic table organizes the various types of atoms into columns based on logical groupings. According to chemical properties are determined by the configuration of the electrons orbiting the atom. Atomic number is defined to be the number of protons in the nucleus of an atom. The number of protons dictates the physical properties of an atom. For example, an atom with 2 protons is helium, an inert gas, regardless of the number of neutrons or electrons. Atomic weight is defined as the sum of the number of protons and neutrons. A specific element always has the same number of protons but may have various numbers of neutrons. For a particular element, a nucleus with a certain number of neutrons may be stable while another nucleus with the same number of protons but a different number of neutrons may be unstable, also called radioactive. Atomic mass unit, abbreviated AMU, is defined as 1/12 the mass of a carbon-12 atom. That is a carbon atom with 6 protons and 6 neutrons. However, atomic mass commonly refers to the sum of the numbers of protons and neutrons for any atom. As you can see, the AMU is approximately the mass of either proton or a neutron, while the mass of an electron is considerably less. Note the designation of the helium atom. The 2 in the lower left is the number of protons, while the 4 in the upper left is the atomic weight. That is the number of nucleons, which is the sum of the number of protons and neutrons. In this case the atomic weight is 4. 2 protons and 2 neutrons. Because the charges of a proton and electron are equal but opposite. In an electrically neutral atom the number of protons equals the number of electrons. Particles with unlike charges, for example a proton and an electron, are attracted to one another, while particles with like charges, for example 2 protons, repel one another. These are called Coulomb forces. This is the equation for the Coulomb force between two charged particles. Equations tell us a story. Here we see the Coulomb force between two particles is proportional to the particle charges. If you double either charge, the force will also double, either attraction or repulsion. The r term in the denominator is the distance between the two charged particles. Since it is the denominator, if the distance increases, the force decreases and vice versa. Note the r is squared. This means if you double the distance between the two charged particles, the force would be reduced by a factor of 4. Another way to say this is that Coulomb forces drop off rapidly with distance. The nucleus on the right has more protons, so it has a stronger attraction to an electron. As we increase the distance between a nucleus and electron, the force of attraction falls off rapidly. An electron has a negative charge and a very small mass compared to a proton or neutron. Electrons orbiting a nucleus are only found in designated shells and nowhere else. The shell closest to the nucleus is called K. And as we move away from the nucleus, the shell designations are LMN, etc. Atoms are mostly empty space. If an atom were a baseball stadium, the nucleus would be the size of a baseball even though it contains most of the mass. It is the electron shells and not the nucleus which dictate the chemical properties of an atom. Each electron shell has a designated capacity. You can't squeeze 3 electrons into the K shell. Electrons are attracted to the nucleus by the Coulomb forces between each electron and the protons. In the nucleus, binding energy is the amount of energy it would take to pluck an electron from an atom. Ionization. Binding energy is higher for inner shells which are close and for higher atomic numbers. Number of protons in the nucleus. While each shell has a designated capacity, it is possible for a shell not to be filled. Shells don't like gaps or vacancies in inner shells. They prefer that each shell be filled before an electron is placed in the next shell out. You can make the atom happy again by filling the unfilled shell. Electrons are mobile. They can move from shell to shell. By providing energy, it is possible to move an electron from an inner shell up to an outer shell, even if it creates a gap in the inner shell. This is called excitation. The amount of energy required is equal to the difference in binding energies between the starting and ending shell. That is the shell where the electron started and the shell where it ends up. A gap in a lower, inner shell makes an atom unhappy. It will attempt to become happy again by eliminating gaps. That is moving electrons from the higher, outer shells down to lower shell. However, electrons can't simply move down. They must release energy to do this, and the amount of energy released is the exact difference in the binding energies of the starting and ending shells. In other words, the same amount of energy it took to kick the electron up to the higher shell. This energy is released in a specific form called a characteristic X-ray. Let's change subjects. Electromagnetic EM. Radiation is the transport of energy through space. EM, as the name implies, has properties of both electric and magnetic fields. No medium is required to transmit this energy, which is a good thing since we get light and heat from the sun through the vacuum of space. Sometimes EM acts like particles, traveling as individual particles, but sometimes EM has properties of waves. For example, EM radiation can undergo refraction or bending. Let's look at EM as discrete particles, which are called quanta or photons. A photon is a bundle of pure energy which we can measure in units of electron volts. An electron volt is the energy an electron would gain if accelerated by a 1-volt potential. Each photon has a frequency which is proportional its energy, so a higher energy photon has an higher frequency. In fact, if the photon energy doubles, so does its frequency. The proportionality between the two is called Planck's constant. EM also has properties of waves, including a wavelength or the distance between successive waves. If you multiply a photo's wavelength by its frequency, you have calculated the velocity of the wave. Velocity in a particular medium for an EM wave is fixed, meaning that wavelength and frequency are inversely proportional. When one goes up by 5, the other drops by 5. Notice that to make the equation on the slide work, you have to have compatible units. You might recognize the velocity of EM as the speed of light. There are many examples of electromagnetic radiation, including X-rays and visible light. They differ in frequency and wavelength. Radio waves have the lowest energy. That means they also have the lowest frequency and highest wavelength. Radio waves are all around us. You know that because your phone in your pocket is constantly receiving signals. X-rays have the highest energy. With a little mathematical magic, one can derive the above equation calculating the energy of photon in keV from its wavelength in angstroms. 1 angstrom equals 10 to the minus 10 power meters. Remember, whenever we see numbers in an equation, that means the equation is unit dependent. This one only works when energy is in keV and wavelength is in angstroms. Wow, we made it!